Hello everybody, welcome to today's COSI seminar. We have Professor Chen Greif from the University of British Columbia in Canada. Chen got his bachelor and master's degrees in applied math from Tel Aviv University. He then moved to British Columbia and got his PhD in applied math, also from the University of British Columbia in Vancouver. He was a fellow, postdoctoral fellow at Stanford, and a senior software engineer in a company, Parametric Technology Corporation, and he's now an associate professor at the Department of Computer Science in the University of British Columbia, and his research focuses on numerical linear algebra and other related topics. So, welcome.
Thank you very much. Okay, great to be here. Thanks for the invitation. This is a talk on solution of linear systems. I've already received some hints that not everybody wakes up in the morning and inverts a matrix. So I'll see what I can do about that. So let's jump right into it if I'm... Uh-oh. I thought that's what I wanted to do. My computer is not letting... that's not good. Just a minute here. I promise you that there's more than one slide in this talk. But I don't know what to do about this.
Iterative solution.
Pardon me?
Iterative solution.
Iterative solution, exactly. Let me try to... Of course, I don't know if you'll believe me. It's not responding. If you'll believe me, that I'll tell you. It never happened before. It had to happen now. If not, then it will be my test. I'll just talk a little bit while... so this is not responding for some reason. Let me try again. There's a bunch of files here. This is called Boulder. Let me try to do that again, and hopefully this time it will go up. Okay, don't send. Okay. So here is the outline of the talk. Very briefly, saddle point systems. I'll explain what these are, then talk about augmentation preconditioners, and then talk about a bunch of applications. And again, a lot of this will be fairly mathematical or computational, and the way I designed the talk, I'll try to give some background on this stuff in a way that I hope will be understandable to people in this audience. So here is the linear system that we're looking at. Okay, so this is a system. It's kind of an interesting system. It looks like this. So even though the A and the B look the same there, it's a font problem. This is our A. Okay, and these problems arise in more settings than you might imagine, and we'll talk about that a little bit. Okay, so A is n by n, and B, which is here, is m by n, and what I'd like us to remember is that m is smaller than n, and interesting, this is quite an interesting linear system that leads to a lot of interesting situations. One of the things that we're going to assume, this is B transpose, is that this is an invertible linear system, but it doesn't mean really almost anything. For example, this matrix A could not be invertible, and this linear system is still invertible, and that makes it very interesting. Okay? So a few properties that I just threw on the slides, but I'll not bother to mention. Maybe we'll get to them soon. These problems do arise in many applications. In fact, if you think of B as a constraint matrix, and we will see that in just a minute, then in almost every problem when you need to minimize something subject to constraints, you will end up with this, more or less. Okay, so we all want to do that in life, right? We all want to maximize our profit subject to a certain risk, say. Okay, and that actually gives us a linear system of this sort. So I just mentioned a few things here, the fluid flow problems, electromagnetic, optimization problems, I'll talk about that. very active area of research. There's a survey paper that came out in 2005 of a very large length, and many people are interested in this problem. Okay, so here is an example. Okay, the steady state Stokes equation. So what we're writing here is just the systems here. That could be in 2 dimensions or 3 dimensions. I should change that. This denotes a Laplacian. In an engineering department that might not be clear, but so the minus Laplacian of a velocity field plus a gradient of a scalar pressure field is equal to some load force, and then a divergence-free condition right here. And if you take this and you just discretize, then in this case it will be exactly this. So you can think of A as a discrete version of the Laplacian. You can think of B as a discrete version of a divergence operator. Okay? Here is another example from a completely different area, but they are related. Minimize X transpose AX minus F transpose X subject to some constraints. And really, I mean, I hope that people have either run into this or they believe me that this is a very general formulation, and often we will see a problem of this sort. Even if the original problem does not arise in this sort, often you will want to formulate it this way. And the constraint could be anything, right? For example, it could be something that tells you something about the smoothness of your solution. You don't want just a solution. You want a solution that satisfies certain smoothness properties. And if you take that and you just refer to it in the usual way, you just define this thing that you want to minimize as part of your problem, and you add Lagrange multipliers times bx minus g, and so you will just have this function. And what we usually do in those situations when we want to find a minimum is, we just differentiate, we equate to 0, we pray, and out comes the solution. And this guy is again that linear system. Okay, so it all leads to that. And this is a third and a last example in this part of the talk, just a little more complicated, semi-definite programming. Many applications. I have a slide later that actually talks about what applications. And again, it's very similar to the previous slide, except the inner products here are a little more complicated. Okay? So again, this is the problem of interest. Okay? Feel free to stop me at any time. This is again something that I'm not going to talk extensively about, but just for the sake of using the terminology that you might run into in the literature, those problems, those constraint minimization problems in the context of optimizations are often solved using interior point methods. Those methods are sophisticated methods that actually go inside your domain. They follow a certain path. And in the end of the day, it's just a nonlinear problem that is based on what is called a primal dual formulation of the problem, a little hairy in terms of the optimization. And what you end up with is equations for the Newton steps. So in each Newton step, you need to solve an equation of this sort, and you can reduce it to an equation of this sort, or a linear system. And again, look at this structure. It's really the same as this structure, except to confuse everybody, now my A is there where the B was, but it's really the same. Okay? So again, just to give a flavor of the richness of applications where this arises. Now, what are the challenges? What are we going to look at? We're going to look at a few challenges here. First of all, those problems, we will assume that they're sparse. Okay, we're assuming that the operators are sparse, and that will happen often when you look at, for example, problems that arise from discretization of PDEs, differential equations. So if you think about it, differential equations being local operators at the end of the day, everything depends locally. When you discretize derivatives, your matrix A and your matrix B in the context of, for example, fluid flow problems are very sparse, okay? The other thing is that there's a very nice structure here, okay? So you can throw that to the garbage. You can just say, I don't care what structure there is here. This is just a linear system. I have a linear solver, and I will use it. But that, you will have to pay a price, okay? I mean, the price is just, when it comes to large-scale problems, it's a high price. It's just a computational price, okay? And more than that, you might get the wrong solution. So you have to be a little careful when you do these things, okay? And the other thing that I already mentioned is that this operator, hey, might be particularly difficult to deal with. It might not be, we might not be able to, for example, invert it. It might be some kind of a crazy operator. You know what? It could have a lot of zeros in it, for example, and still we want to be able to deal with it, okay? So these are the challenges. And again, just to emphasize the last point, a singular matrix A, a situation in which you cannot invert this operator, arises in many situations, a few of which I'll discuss in this talk, okay? So that will come. So in fact, there's just kind of a laundry list here, but some of these things we will see in later slides. I'll actually spell out the applications specifically, okay? So let's just focus on what we're interested to accomplish right now, and that is to look at a linear system of this sort. I hope that everybody's convinced or semi-convinced, or at least is being polite and is not objecting to the fact that there are many applications in which these things arise. And let's just throw that to the side for a minute and ask ourselves, how can we solve these problems? Of course, we want to look at the underlying model where it came from. We don't want to forget where it came from. But let me show you a few possible manipulations. Let me just say something about being a numerical analyst. The nice thing about doing numerical analysis is that you can do simple stuff that a mathematician will laugh at you for doing, and you can still claim that it's a great thing, okay? That numerically you accomplish something amazing that you couldn't accomplish before. And here is an example, okay? No mathematician will be impressed with multiplying the second block row by -1, right? I hope. But in fact, this is a manipulation that changes completely the system numerically, okay? So, for example, unfortunately I can't ask the audience because the answer is on the slide. For example, suppose A was symmetric. 0 is also a symmetric operator. B appears with its symmetric counterpart, B transpose. So if A is symmetric, this whole thing is symmetric as well. But if you multiply this guy by -1, you lose symmetry. This is very significant, extremely significant for iterative solvers, okay? So for example, just to say something that I'll talk about later, if you have symmetric operators, you can actually solve linear systems much quicker than if they're non-symmetric, okay? On the other hand, this when you multiply by -1 is positive semi-definite, which means that every inner product with any non-zero vector will give you something that is non-negative, which doesn't happen for the original symmetric matrix. So you have an interesting trade-off here. You either have symmetric but indefinite, yes?
Sorry, so that's including the A? So what are you assuming about A, or you mean just the B and B?
No, I'm assuming that A is symmetric. So even if A is symmetric, when we do this manipulation, the matrix here is not symmetric anymore, okay? But it's positive semi-definite, okay? And that's actually something that you can prove simply by trying out the inner products, okay? So that is something that allows you to use versions of conjugate gradients for those of you who are a little more familiar with those methods, whereas the original matrix, even though it's symmetric, you cannot use conjugate gradient because it's not positive definite or semi-definite. It's just indefinite, okay? The other manipulation that you can do is you can take separate the symmetric and the skew-symmetric part of your matrix, and there are methods to deal with that. So you see the wealth of of methods that just by a simple-minded manipulation, and that's really what happens in those numerical methods. Here is another important manipulation, something that is used by people who do finite element methods for fluid flow problems, and that is to replace the zero by a semi-definite matrix C with a minus, so that would be negative semi-definite matrix. And this is called regularization. The thing that to remember is that this one is actually different than the previous one. In the previous one, you did not change the solution. Okay? You just multiplied by -1, accordingly also on the right-hand side. Here you are going to change the solution, but that gives you another, again, a wealth of solution methods. Okay? And that might stabilize the problem, might make it a little easier to solve. Here is another one of my favorites. In fact, this will make an appearance in the talk quite a lot. And here is another one of those things that look amazingly naive, but in fact changes completely the situation. So let me just illustrate that here. So you have AX plus B, I'll just stick to the notation here, so that's a lambda there, is equal to F. And conveniently, I wrote a 0 there, even though it doesn't have to be a 0, and Bx is equal to 0. So what I'm going to do now, remember that this matrix, this is a transpose. This doesn't even match in terms of sizes. I'm going to take my Bx, and I'm going to multiply it by B transpose. And that's allowed. It's still 0 on the right-hand side. And now I'm going to take that 0. So in numerical methods and in life, it's allowed to add a 0 to an equation. So I will take this 0 and I'll add it to my equation. And that is completely legit. And this one stays. So what did I do? Nothing. I added a 0 to the equation. Okay? Now what happened? For example, if A was singular, maybe this matrix is not singular. Okay, so here is a huge benefit that you can get out of doing that. What is a disadvantage? Maybe this matrix has a very bad structure, B transpose B. Okay, maybe it has a bad condition number. It has all kinds of bad things. So again, you have to be careful. But the manipulation is possible. And this is actually related to something called augmented Lagrangian, a stabilization method. And again, if we go back to these 3 manipulations, this belongs to the first class. The first manipulation, multiplying by minus, does not change the solution. Second one, regularization, does. Third one does not. Okay? We just add a 0. That's how I would like to think about it. And then we can add a lambda here or anything else. Or a W in the middle. We can multiply by a W here and stuff like that. This goes back to the 70s, but it's actually in the context of an application, a popular approach. Okay? So I would like to talk a little bit about Krylov subspace solvers. This is Alexei Krylov. And I don't know if any of you thinks this is a faked picture. He lived a little before I was born. So I would have liked to meet with him, but I haven't. And here is the basic idea of Krylov subspace methods. Okay? And min-res, which is a method that I'll use, can be explained very briefly along the following lines. Modern iterative method, first of all, before I even jump there, I want to make the point that because of sparsity, because of structure, because I want to exploit what I know about these operators, I will avoid just performing something that we all know how to do, like Gaussian elimination. I will not, this is not the interest right now. This is not to say that these are not good methods, but I will not just start performing row operations on this matrix to get a solution. Instead, I will assume that the matrices are so large that I would like to base everything on matrix vector products. This will be my atomic unit, okay? There will not be any factorizations of any sort, just matrix vector products. And Krylov subspace methods, the beauty of them is that they work inside a space, a very special space. And that space is defined here, okay? Now this is the topic of at least one graduate course, if not two, if you want to lay out the whole theory of Kirillov subspace solvers. But the basic idea, the elevator conversation, is the following. Suppose you want to solve FU is equal to B, form the initial residual, take an initial guess U naught, form an initial residual, and then look for solutions inside the following space. The initial guess plus a space that is spanned by the initial residual and powers of your matrix. Okay? Now it can be shown that if you take this all the way to a dimension of the size of the matrix, you will always converge if you apply the right optimality criterion. Okay? But the key is to, suppose you take a million by a million matrix, the key is to perform very few iterations. So what are these methods good for? They're good for, we're going to do the following. We're going to look for a solution. This was the kth iterate, which is again a sum of the initial guess plus powers of the matrix times the residuals that are defined here. And we're going to do that so that B minus F times UK is minimized. Okay, now just to make sure that everybody is with me, if UK, U sub K, is equal to U, then we're done. The norm is just 0 and we're done. Okay? So what we're going to do though, we're going to use those methods to tell ourselves, I don't care that when we're done, I care how long will it take me to get a residual that is very small. That's what I'm up to, okay? And it turns out, so again, based on matrix vector products, symmetry, very important. So remember, I made that comment. Here is where symmetry allows for very short recurrences. You can actually do that very, very quickly, okay? And preconditioning is absolutely crucial. So what is preconditioning? This is the next slide. So preconditioning is based on observing when do these methods excel, okay? So when do they excel? So again, I just want everybody to understand that this is the method. We haven't spelled out the methods. These methods have a nice thing that within 10 or 12 lines you can actually spell them out here, and they're very, very elegantly short, okay? And in order to accomplish anything there, we want the residual to be small. Now, here is the point. The operator is given to us. Nobody has promised us a garden of roses or wherever that goes. They give us an operator and they tell us to deal with it, okay? So what we want is we want to identify properties of these methods that will help us converge fast, okay? So it turns out that one of the most significant property of all is the following. If the matrix has only very few eigenvalues, then those methods will converge fast. In fact, the number of iteration will correspond to the number of distinct eigenvalues. Okay? Now, how, yes?
What do you mean if the matrix has very few eigenvalues? Very few unique ones? Or?
Very few distinct ones. Thanks for asking this question. The matrix, let's say, is 1,000,000 by 1,000,000. Okay? Let's say that it has only 3 distinct eigenvalues, meaning that it has the eigenvalues 1, 2, and 3. That means that each of them is a multiple eigenvalue. So for example, one of them will be multiplicity of 500,000. The next one is a multiplicity of 250,000, and the third one is a multiplicity of 250,000. So if you think of the identity matrix, it has only one distinct eigenvalue. That's the eigenvalue 1, but its multiplicity is of the size of the matrix. Here I'm talking only about the distinct ones. Okay? Now, because of that property, if we have only 3 distinct eigenvalues, in the absence of a round of errors, we will converge within 3 iterations. Okay? So now, what we do is we tell ourselves this is a wonderful property, but our operator f, we have no control over it. For example, these problems that I showed you earlier, there are tons of eigenvalues. We have no control over this. What we will do is we will multiply this f by an operator of our choice, we call that a preconditioner, so that M inverse F has only very few eigenvalues. Can we do that? That's the question. This is why preconditioning is not only a science, it's a bit of an art if you think about it, because what you want is you want something that behaves like F, such that M inverse F, it's kind of like a contradictory thing. On the one hand, you want M to be very much like F. On the other hand, you want to work much less for M than you want to work for F. Okay? So this matrix, M inverse F, is now in our control. You give me F, I will give you M that makes those eigenvalues more clustered. We'll try to generate only a few distinct sets of eigenvalues or a few clouds of eigenvalues. Okay? And that's really what stands at the basis of these methods. So feel free to stop me anytime, of course, if something is not clear. Okay? So let's go back to that manipulation that we discussed, that is laid out on the board, and let's talk a little bit about that. Okay, so let me say a few things about that. So basically, so Gene Golob is sadly no longer with us. He was my mentor at Stanford, and we started a few years ago, already in 2003. We looked at the spectrum of these matrices, and we discovered that when you put a gamma here, when you just put a gamma here, then when you take gamma to be very, very large, then all the negative eigenvalues of the matrix tend to cluster near -1 over gamma. So the reason I'm mentioning that is because this is the kind of manipulation that you want to do. You want to actually generate a better spectral structure for your operator. Okay. Okay. This is the idea of all these things. Okay. So let me maybe I'll skip that in the until when do I have Ariel? Until 10 to 5. Okay. So let me skip that. Sorry? Yeah. Let me skip a few of those and talk a little more about these preconditioners and tell you what kind of preconditioners are there. So this is the matrix that we're looking at. Okay, this is the original matrix, and there are three very popular types of preconditioners, and the one in red is the one that I'll focus on. It's related to this manipulation. And all of them are based on approximating something related to the inverse of A. This is a very important matrix. It's called the Schur complement. Okay? This is called constraint preconditioners. Notice the very nice property of this is that the constraints themselves do not change throughout the solution, and this is something that optimizers love because it means that you always satisfy the constraints throughout. You only change your A. And this one is based on what I just said, this manipulation that really could change things for the better, for example, if A is positive definite. Okay? So let me, for example, talk about some work that I've been involved with a few years back, and that is that third preconditioner. If you look at this matrix, again, in the context of what we called F and M, this is F and this is M. And what we want is that M inverse F will have only very few eigenvalues. Okay? So this is exactly what happens, it turns out. So there's a theorem that actually says that there are many, many eigenvalues, an eigenvalue of a very high multiplicity that is equal to 1. And there's an eigenvalue -1 of a very high multiplicity as well, and basically this is the core of that, and I'll call it the blessing of nullity, and that is the more singular A is, in the end we get only two distinct eigenvalues, 1 and -1. Okay? So basically here is what I'm saying. What I'm saying is that if you accept the notion that what we want is to use those iterative methods in a way that we will multiply our matrix F by a matrix M inverse, such that M inverse F has only very few eigenvalues. Then we're in luck here. We have only 2 iterations, okay, and we're done, okay? And I hope nobody believes me that it's that easy, okay? So, you know, it's not so easy to use these preconditioners. In fact, it's a can of worms. Why? Because it involves solving this, okay? So here is, so, you know, in a funny way, it's kind of like sweeping all the dirt under the rug. We now say, great, we don't need to deal with F anymore. We don't like F. F is hard to deal with. Let's deal with M, okay? And now M inverse F is nice. But what about dealing with M? Maybe M is hard to deal with. It is hard to deal with, okay? So what we will need to do is we will need to approximate this in an effective way in order to make progress. And this can be done. It depends on the problem. Okay, so here are a few applications, and this will be the second last part of the talk, and I will scan through them and show only a few. There's tons of them here. I already told somebody before the talk there are too many slides, and I will just look at a few of them. Here is the Maxwell equations in its full glory, or the Maxwell equations in mixed form. And I don't know how many of you deal with those things. I'll just mention the things that make it difficult and interesting. There's a curl-curl operator here. This is an operator that is very, very singular. Okay, so those of you who deal with Maxwell equations know that this is a problem here. And that is because a curl grad is 0. And so you have a big null space here. Okay, this is the B matrix. Looks very much like what we showed before for fluid flow, okay? And there's a bunch of things here. And if you discretize this, this is what you get. A is that curl-curl operator, okay? And B is that div operator, okay? So this looks exactly the same as here, except this minus k squared m that is there. And guess what we will do? We will assume that k is equal to 0, because we're not smart enough to deal with that. Okay, so A, B transpose B 0. This is the combination of work, much related work, and a few key properties that in the name of time I will skip, but I want to show you one thing, and that is that in fact, in the end of the day, we can do this, except we want to replace this by something that is easier to solve, okay? So what we do to solve that is basically to take all this matrix, this big matrix, and I don't know to what detail I want to get into it. The matrix L there is a Laplacian, and we're going to replace all this matrix by a mass matrix, which is just an identity operator, and we have a lot of theory to support what will happen if we do that, okay? And so this will be our preconditioner, and I want to make a point in just a minute. Remember what I said earlier, and that is that we will have only 2 eigenvalues, only 2 distinct eigenvalues. Now, this is a graph of the eigenvalues using that preconditioner, and it doesn't quite look like there are 2 distinct ones, but it's not bad, okay? You see this spillover here. And that's because we're not going to use this operator exactly. We're going to approximate it. And that's part of it. It's, again, that can of worms that we're trying to avoid. We're trying, on the one hand, to realize that we only generate an approach with very few eigenvalues, but at the same time to make sure that we don't work so hard to solve that problem that it completely defeats the purpose. Okay? So we have, an iterative solver will not quite converge in 2 iterations, but it will converge in a few iterations. That's because essentially many of the eigenvalues are concentrated here and many of them are concentrated here. Okay, and this is exactly what happens. Here is just an illustration of meshes on which you work with. And what you end up with is something that is very, very nice and stable, okay? 5 or 6 iterations throughout. And that's really because of that loss, okay? So we don't quite get 2, but it's not bad, And that's exactly what we want to see. So here are a couple of quick examples. This is work with Dan Lee, who is my PhD student, and she deserves to be bold-faced. She's done a lot of the work here. And just a couple of complicated geometries, and go up in dimensions, some information about the solvers. So this is a large-scale package that actually uses this preconditioning approach. And what I want to show in this slide is the following. So first of all, how many degrees of freedom do we have? This is the size of the matrices. Okay, so we go all the way up to 20 million. I think now we can solve 40 million. And the important thing is to see the number of iterations. Okay, so the number of iterations stays the same. Okay, and this is what we want to see. We want to see that the number of iterations does not go higher. That really means that we managed to do that clustering that I talked with you about. This is information about the time. There's an assembly for finite elements. It's very nicely scalable. And then there's some increase in the time it takes to solve these things when we increase the number of processors. So this is done in parallel computation fashion using 3, 6, and 9 processors, 20 million unknowns. And it takes a while, but it's not bad. It's not bad. And it scales very nicely. And this is the type of things that we want to show. This is for the other problem. There's not much to add here. Okay, let's see. I have a few more examples. I don't want to abuse the time here. So let me make a quick decision here and skip over a few. So there's a magnetohydrodynamics problem that is built on that, and maybe I'll skip it. And there's some recent work that I did with Michael Overton. Maybe I'll skip it and just show a couple of graphs, okay? So here is a graph that illustrates what's going on. So basically, this is related to an optimization problem, okay? So in optimization, as I said at the very beginning, you have a similar situation. You have a problem with constraints. You walk inside your path. There's something called a centering parameter. You're just following the central path, it's called, until you hit the solution. Now, what are the properties, what are the attributes of these problems? These are hard problems, okay? Each linear system that you solve corresponds to a Newton step. And what happens is that when you get very, very close to the solution, your problem becomes very, very singular. Okay? In fact, at the limit, at the solution, the 1-1 block is maximally singular. Now let me take you back to that slide that I called blessing of nullity or blessing of singularity. And that is where I said that if the operator is singular, you will have exactly 2 distinct eigenvalues. So in a funny way, exactly when the problem is harder, this preconditioning approach might tackle it better. This is not to say that this is a better preconditioning approach than others. It's just tailored to situations in which you have high singularity. And that's the beauty of preconditioning approaches. I will not stand here and say this is the winner or this is the loser. There's no point to do that. All these preconditioners are fairly effective depending on the underlying properties of the problem. So when you look at the eigenvalue distribution, you see at the beginning of the preconditioning approach, you see at the beginning that there are some eigenvalues, but there are more groups. This is just a toy illustration of that. Groups of eigenvalues. This is iteration 1. I don't know if you can see, it's written there. Then in iteration 6 of the optimization, so in every iteration of the optimization you need to solve a linear system, you see that those eigenvalues take a stand. You know, it's kind of, they go to a camp. You know, there's a lot of them that were here. Many of them just go here. And then when you're very, very close to the solution, you're really starting to see something that is very, very clean. So here is the difficulty, though, and this is another graph, and I hope that it can be seen nicely. This actually tells you how many iterations it has taken. Okay? So what happens is that very close to the solution, because of that singularity, you will converge nicely. This is just a few test cases. At the beginning, the problem is fairly well conditioned. So you are doing okay. But in the middle, you're not going to do so nicely. Just to make sure that it's clear, these are iteration counts for each of the optimization solutions. But if you scale things the right way, you could stay within a fairly good number of iterations here. And this is what is shown here. Okay? So again, these preconditioning approaches can actually improve the situation. Okay, so let me, here is another example that shows exactly the same thing for a semi-definite programming problem. These are the original eigenvalues. These are the positive ones, and the red ones are the negative ones. And after you apply the preconditioning approach, you make them line up, more or less. Some of them are stranded there. They will cause problems. You will always have problems. Here are a few that are stranded there. But altogether, a lot of them are nicely clustered. Okay? So I think this is the right time to stop. So in summary, here is what I wanted to talk about today. First of all, just to illustrate the point, or to make the point that those saddle point systems are important. You might run into one when you walk in the street next time, so don't be afraid. Just overcome it, you know. Throw a preconditioner at it and tame it. They do arise in optimization. They arise in the solution of partial differential equations. Iterative solution is very good for large and sparse problems. If you have a very nice structure, if you have differential operators or something like that, if you want to exploit the structure, okay, and if the problem is huge and all you can do is matrix vector products with it, you cannot really perform a Gaussian elimination thing or something that we know how to do but is a little hard, then you want to do iterative solution, okay? But as we said, it's not enough to apply an iterative solver for this, because the performance of these guys depends very, very strongly on the spectral distribution of how the eigenvalues are posed. And our main goal is to make the eigenvalues as clustered as possible, to generate strong and dense clouds of isolated clouds of eigenvalues. How do we do that? It's hard, because the best preconditioner is the operator itself, and that's ridiculous, okay? The easiest preconditioner is the identity matrix, and it does nothing. What you want is something in the middle that on the one hand approximate the operator well, but on the other hand makes it much easier to work with it. And this is really the message here. And to do that, there is a very large class of methods, block preconditioners based on Schur complements, and one of them I try to illustrate a little more. Okay, so thanks very much.
Questions?
Yeah.
How much theory, as opposed to empirical investigation, is there behind some of these phenomena? For example, stranding of eigenvalues. Can you predict when that phenomenon will occur?
Yeah, there's a lot of theory. In fact, I might be doing injustice, you know, in this talk, which tries to just give a flavor and give some computational illustration. I might be doing some injustice. Let me qualify my answer. You know, for the tough problems, the really tough ones, it's probably impossible to know even the first thing about the spectral distribution for the original problem. So before I even dive into preconditioning, I don't know anything, okay? What you will see in many numerical linear algebra papers is somewhere after stating the problem in its full glory, there will be a small line saying from now on we will assume constant coefficients. And for that you can actually obtain reasonable, so for example, we've managed to obtain reasonable estimates for convection diffusion equations with constant coefficients, which might not be satisfying. Now the stranded Eigenvalues, you can get a certain sense. You will not know where they are, but for example, in that graph that I showed, which followed 5 slides that I had skipped, there's a theory that says there will be exactly 3 stranded eigenvalues. We don't know where they are, but for all practical purposes, we just give up on them. So it's kind of a qualitative thing rather than quantitative. But altogether, there's a fairly solid theory for the easier problems.
So I'm just wondering, so when you have these stray eigenvalues, they're going to be giving you some error in the solution? Is that the
No, they will just delay convergence. All they will do, okay, they might. Let me again qualify the answer here. If they are just like here, the stranded ones, they're not bad. I apologize for I don't know if you can see the numbers. This is 10 to the 1, this is 10 to the 0. This is 1. This is where you want all your eigenvalues to be. The stranded ones are of the order of 10. This is fantastic for all practical purpose, but this is a tiny problem, okay? So, if the eigenvalues are stranded but they're not in terrible locations, they will just delay convergence. In this case, what will happen, and that's the interesting thing, I could claim, and I will be reasonably correct, to claim that this method will converge in 8 iterations. And here, let me illustrate what I mean. 1, 2, 3, 4, 5, 6, 7, 8. So I will pay a huge price for all these stranded ones that are not in the exact place, and I don't want to get into arguments. I mean, how close are these? So basically, we'll pay 1 iteration for each of these. It will delay convergence by a lot. For each of these stranded eigenvalues, you will delay convergence by 1. If these eigenvalues, if what was written there was not 10, but rather 10 to the 7, which does happen often, if those stranded eigenvalues are out there, then it will also generate error in the solution. So you will not only converge more slowly, you will also be, you're prone to some errors. Yeah.
So I was wondering, you said you add the gamma BTD, so it looks to me like basically you want to solve for A, but then you add a gigantic gamma, and what that does is basically make that top left corner look like 1 plus x, where x is a really small number, but x is what you wanted to solve in the first place. It's kind of like you're doing a Taylor series in A or something.
Yeah, well,
I don't know if that's because you have like b on the left, b on the right. It looks like you just multiply gamma and 0 diagonal matrix with the
right.
when A is not there.
Right. Let me tell. Yeah, go ahead. Sorry. Yeah.
I'm just wondering, is that a good thing to sort of dwarf A?
Yeah, it's. I'm really glad you asked, because let me go back to a slide that I skipped. Okay, it's always nice to get a question that then I'll say, oh, but I have a slide to illustrate this, and I do have a couple minutes for that, right? So let me just. This is one slide that takes a little while to explain, and I didn't want to go through it. But what you're saying is absolutely right. What happens is, but it's not necessarily a bad thing. So here is what I'm going to say. What this graph shows is what I'm going to do. I'm going to start with the worst possible situation. That's the situation of A being singular. So if A is singular, you want to dwarf it, because it will not give you anything. It will not be possible to work with it. And then, in this case, adding something to balance it is good. What this graph shows, in fact, is, and it's a few matrices here, but look at the green, look at the red one. It's the most interesting one. This is something that measures the condition number of A plus gamma B transpose B. So when it's singular, it's infinity, and there's nothing you can do about it. It's bad. So let's just consider this as infinity. This matrix is also singular, so you might dwarf it in such a terrible way that you will have a very bad guy dominate as well. What you really want is you want, and this is what I'm taking from your comment too, you want a moderate value of gamma that will actually be able to make a good effect on A without a terrible effect of B transpose B. And then it's okay, because then you go back to the algebraic. Then what I'm saying is, look, I have not changed the solution. All I did is I did a manipulation. It's true, though, that if gamma is too large, you will get a terrible error. I absolutely agree with you, and I think this is a very thing to worry about. And those graphs, I explained only about the red one, but this is the condition number of this original matrix, the whole matrix, when you start adding gamma B transpose B. So notice that there is this one area here when everything is great. This is the condition number of A plus gamma B transpose B is okay. The condition number of the whole matrix is still okay. It's not starting to go up. But the moment you overdo, you will get terrible errors. So you really do need a small value of gamma. But if you settle for a small value of gamma, then you're okay. Does this answer? Yeah.
Sure. Given that I don't know anything about the field.
Okay.
And then, so the other question is, so basically, what's the algorithm? So you have this matrix which describes your problem.
Right.
So you have to pick a gamma, but A, B are given.
Right.
So do you pick a gamma, or is it always 1?
No, that's a great question as well. So gamma, in this particular case, in the absence of any knowledge whatsoever, typically gamma will simply be the ratio between the norm of this matrix and the norm of this. Just a balancing act. That's all. If you know a little more about gamma, you can actually replace it by a whole matrix. And this matrix could be like a differential operator, and then the considerations are much deeper. Okay? And in the Maxwell problem, we have a much deeper set of considerations based on in-soup conditions, all kinds of things related to PDEs. But the simplest thing, in the absence of any knowledge, just balance this with this. If A is of order 1 and B is of order 100, take this to be 1 over 100, so that these things are balanced. And this is really amounts to a moderate value of gamma. So that's a good point to mention. What is that value? You need to know it. Yeah.
Any other questions? So
Yes.
if I have a problem,
Yes.
where do I start? Most engineers will go and look into the MATLAB toolboxes.
Yes.
Up there, they pick whatever is there. So
Yeah.
So there is a mismatch between the things that we do and what we need to solve problems, and then we don't know where to start.
Yeah.
We can call you. I can call you.
Definitely, please do, or come and visit me. Yeah. Yeah. Here, let me just say something that I think is very important, which doesn't really answer your question. But let me start by saying how important it is to solve these problems efficiently. Because if you start in the wrong foot, you will really you could spend a week instead of 5 minutes on solving these things. And this is what happens if you, for example, call MATLAB without knowing. Seriously. So unfortunately, my answer to your question is, read a good numerical linear algebra book. Some of them are really nice bedtime reading, light reading. But you need to spend some time just classifying. Now, just to give a more serious answer, you don't need to know the ins and outs. This is what I kind of do for a living. I like to actually get into the theory of these things. You don't need to know that. What you want to know, you want to classify your problem according to a few very, very basic parameters. Is the problem symmetric? If it is it positive definite or not? If it's non-symmetric, there's a couple of other, is it normal? In the end of the day, if I sit with you for 5 minutes, I will be able to define about 5 parameters, of which I just mentioned 3 or so, to classify. And once you have that basic classification, is it large and sparse, or is it dense and small? Is it narrow banded or not? So you have about 5 or 6 or 7 criteria. And if you just know the answer for each of those problems, you know what method to use. And MATLAB gives you all these methods. In fact, it gives you PCG, it gives you MinRes, it does give you these things. And it will actually be nice enough to warn you sometimes if you apply the wrong method, but not always. Sometimes it will just do it. So you know, it's an optimistic message here. There's not that many parameters in the end. You just need to know a few. But it's worth knowing them. You know, here I am with the big message. It's worth knowing. Linear system solve is the absolute computation bottleneck in almost every problem you will solve. Seriously, in the end there will be a linear system waiting for you to be solved many times over. If you solve a nonlinear problem, you will have to solve maybe 20 of those linear systems. So it is worth spending that time and classifying according to those 5 or 6 parameters.
Any other questions? Okay.
So with what you're doing, I guess, I don't know if you kind of summarized for us, so what sort of performance improvement basically do you get over, let's say, me plain vanilla inverting the matrix, or, you know, what's the state of the art? And then the second part of that is, so this is for, I guess, a real number symmetric matrix?
Yes.
So does this extend to complex symmetric?
It does extend to complex Hermitian. So you don't want only symmetry, but also conjugate complex values there. It is harder to extend it to non-symmetric, even though you could. Now, in terms, so again, but you'd have to use a different method, and those short recurrences you cannot use. In terms of how much improvement, it's actually significant improvement. It's not only what I do. I want to make sure that it's clear that a lot of people, so if you look at these tables that I showed at some point during the talk, this is where it is. The fact that when you increase the number of degrees of freedom, you do not increase the iteration counts. If you used a very simple conjugate gradient without spending much thought, this will go up by the factor you increase your mesh. So this is where the improvements are, and it's very, very significant, very significant. Now, there are methods that can do that. So the nice thing is that we know that we can do that if we try hard enough. If I told you now that you can actually decrease the iteration counts, I'll be lying to you. So it's just a lie. So we know that this is the best we can hope for, and in many of those problems we can actually accomplish that, but it's not so easy. You really need to look for those preconditioning approaches that did that. If you didn't do that, this would be, I think, at least 64, if not more. It really depends on the factor when you increase the mesh. Yeah.
When you do this in parallel, so these kind of computations, are they CPU or memory bandwidth, like for making parallel processes?
They are, there is no issue of memory just because we just don't go high enough when memory becomes a huge issue. A lot of the things to remember is that this is one nice thing about matrix vector products, is that they're nicely parallelizable. So you can actually send a chunk of your matrix to a processor, and you can obtain scalability. But to do the preconditioning solve, you cannot scale it quite that well. So in the end of the day, I would say that memory is an issue, and also the ability to parallelize is not there for the preconditioning stage, not completely there. You really have to work hard, but as you can see, you do lose a little bit of time as a result of that. You see, these are times. And the times don't quite stay. We would like them to stay where they are, but they're not. But that's not the result of a memory issue. That's more of just the algorithm cannot parallelize in a maximal fashion, cannot scale completely. Yeah, thanks.
Okay. Let's thank Professor Greif again.
Thank you very much.